JWST unveils a steam-world planet with a water-rich atmosphere. GJ9827d changes our view on exoplanets. The James Webb Space Telescope, JWST, has just uncovered one of the most extraordinary finds in modern astronomy, a steam-world exoplanet orbiting a star just over 100 light-years away. Named GJ9827d, this planet has an atmosphere that's almost entirely composed of water vapor, a condition that scientists have only theorized about until now. Observing such an atmosphere is an unprecedented event, marking a major milestone in our understanding of exoplanets and their atmospheres. This discovery brings astronomers closer to understanding the diversity of planets beyond our solar system and sheds light on previously uncharted territories of planetary science. A unique discovery, GJ9827d. The discovery of GJ9827d's atmosphere is a leap forward in the study of so-called sub-Neptunes, planets that are larger than Earth but smaller than Neptune. Sub-Neptunes are the most common type of exoplanet found throughout our galaxy, yet, intriguingly, there is no analog in our own solar system. GJ9827d, with a size twice that of Earth and a mass nearly 3 times greater, is one such sub-Neptune. However, unlike most sub-Neptunes, which often have atmospheres dominated by light gases like hydrogen and helium, GJ9827d's atmosphere is thick with water vapor and metals, placing it in a category all its own. This steam-world exoplanet orbits a K-type star, a cooler, orange-hued star in the constellation Pisces, which has made it accessible to both past and present telescopes. First detected during the Kepler Space Telescope's K2 mission, GJ9827d has been studied intensely in the years since, with the Hubble Space Telescope even capturing hints of water vapor in its atmosphere. However, it was JWST's advanced spectroscopic capabilities that ultimately revealed the planet's true nature. Transmission spectroscopy and the role of JWST. The JWST achieved this remarkable observation using a technique called transmission spectroscopy, which analyzes the light passing through a planet's atmosphere during its transit in front of its star. Each molecule in an atmosphere absorbs light at specific wavelengths, leaving distinct signatures that can be measured by powerful instruments. For GJ9827d, JWST employed its near-infrared imager and slitless spectrograph, NIRIS, along with its single-object slitless spectroscopy, SOSS, mode, to capture the molecular composition of the atmosphere. The findings revealed an atmosphere that's at least 31% water vapor by volume, an astonishing number that surpasses any exoplanet atmosphere previously observed. This water vapor, combined with high levels of metallic elements, has created an entirely new category of planetary atmospheres. And by observing 2 transits of GJ9827d, JWST provided data that resolved a key ambiguity in exoplanet atmospheres: the Clouds-Metallicity degeneracy. Breaking the Clouds-Metallicity degeneracy. For years, one of the major challenges in studying exoplanet atmospheres has been distinguishing between high-metallicity atmospheres and atmospheres obscured by clouds. Both conditions produce similar spectroscopic features, muted or flattened signals that make it difficult for scientists to identify molecular components. However, JWST's extensive wavelength coverage and sensitivity finally enabled astronomers to break this Clouds-Metallicity degeneracy. The research team, led by Piaulet-Ghorayeb from the Trottier Institute for Research on Exoplanets at the University of Montreal, combined data from JWST and previous Hubble observations to make this determination. This collaboration of telescopes provided a clearer picture of GJ9827d, revealing that the atmosphere's muted features were not due to obscuring clouds, but rather a high concentration of heavy elements. This is the first time astronomers have conclusively observed a high-metallicity, water-rich atmosphere on an exoplanet. What a steam world means for exoplanet science. GJ9827d's atmosphere represents a breakthrough in the study of atmospheric diversity among exoplanets. Most characterized exoplanet atmospheres contain lighter gases, resembling the gas giants in our solar system. The atmosphere of GJ9827d, in contrast, is rich in heavier molecules, bringing it closer in composition to terrestrial planets like Earth, Venus, and Mars. Although GJ9827D's atmospheric conditions make it inhospitable by Earth standards, the discovery suggests that planets with atmospheres rich in heavy molecules might be more common than previously thought. "This is the first time we're ever seeing something like this," said Eshan Raoul, an astrophysicist who analyzed the JWST data on GJ9827D as an undergraduate at the University of Michigan. Raoul described GJ9827D as a steam world, emphasizing that its atmosphere is unlike anything we've encountered before. While this particular planet is unlikely to support life as we know it, similar planets with heavy molecule-rich atmospheres may become targets in the search for habitability elsewhere in the cosmos. From theoretical to observational, steam worlds and life, the idea of steam worlds has floated in the scientific community for some time, but until now, no observational data had confirmed their existence. Some astronomers have speculated that life could exist in the cooler upper layers of a steam world's atmosphere, where temperatures might be more conducive to the formation of complex molecules. However, others remain skeptical, arguing that the extreme conditions on these planets would likely prevent the development of life. What GJ9827D has made clear, though, is that water vapor can dominate an atmosphere in a way scientists hadn't previously confirmed outside computer models. Its discovery represents a new frontier in understanding how planets form, evolve, and interact with their host stars. And in a larger context, it raises fascinating questions about what types of environments might be considered habitable by extraterrestrial standards. The future of exoplanetary science and JWST's role. Ryan McDonald, an astrophysicist and NASA Sagan Fellow at the University of Michigan and a co-author of the study, noted that the JWST's early observations have already begun to reshape scientists' understanding of exoplanet atmospheres. Even with JWST's early observations in 2022, researchers were discovering new insights into the atmospheres of distant gas giants, McDonald said. These early studies primarily involved atmospheres made of lighter gases. But with GJ9827D, JWST has helped scientists look deeper into sub-Neptunes, shedding light on the mysteries of these in-between worlds. This advancement is part of a larger journey toward the ultimate goal of detecting habitable exoplanets. Sub-Neptunes, being the most common type of exoplanet in the Milky Way, are especially valuable targets in this search. Although no sub-Neptunes exist in our solar system, understanding their atmospheres brings us closer to identifying the characteristics of planets that might support life. Now we're finally pushing down into what these mysterious worlds with sizes between Earth and Neptune, for which we don't have an example in our own solar system, are actually made of, McDonald said. This, he explained, is a critical step toward characterizing planets with more complex atmospheres, possibly containing conditions that could support life. Behind the scenes, atmospheric retrieval and the power of modeling, the discovery of GJ9827D's unique atmosphere wasn't a simple matter of observing its transit. It required an extensive process known as atmospheric retrieval. JWST gathers massive amounts of data, and translating this data into an accurate picture of an atmosphere's composition requires complex modeling and machine learning algorithms. Atmospheric retrieval involves comparing observational data to millions of model atmospheres until a best-fit solution is found. Raoul, who now works on his doctorate at the University of Wisconsin-Madison, used software developed by McDonald to conduct this process for GJ9827D. By simulating millions of possible atmospheric scenarios, Raoul was able to identify the model that most closely matched the JWST data, a model that indicated a water-rich, steam-dominated atmosphere. "It was a very surreal moment," Raoul said, reflecting on his first glimpse of a confirmed steam world. The implications of his work extend beyond a single exoplanet. They provide a blueprint for detecting and studying other planets with similarly unique atmospheres. A new era of exploration and discovery. With each discovery, the JWST is pushing the boundaries of what we know about the universe. The revelation of GJ9827D as a steam world exemplifies how far we've come and highlights the potential for even more exciting discoveries on the horizon. While GJ9827d is likely inhospitable by Earth standards, the techniques and knowledge gained from its observation pave the way for identifying other worlds that may have the conditions necessary for life. As we refine our tools and expand our understanding, GJ9827d reminds us that the universe is far stranger and more varied than we might have imagined. Steam worlds may be just the beginning. Who knows what other wonders await our discovery? The journey to understand exoplanets and their potential for habitability is only beginning, with JWST leading the way in this remarkable era of exploration.